Hello everyone, this is Nick here, and I'm going to be showing you today how to find the side length of an equilateral triangle using a circle that is inscribed inside of it. So this I've seen multiple videos, circles outside of triangles, circles inside of triangles, and you get all three of the sides, but I haven't seen a video on this yet. There's probably a few out there, but I decided to make this video. I'll give you the formula straight up if you want it. I can give you the formula. Let me find it here. Oops. So yeah, this is the formula here. So if this is all you're looking for in the video, that's the formula right there. If you're interested in actually looking through how we find this and getting into some geometry, some interesting math here, then I advise you to continue watching because it'll be a fun ride here. So I'll say this. Let's see. The prerequisites for this, if you're watching this video, you need to understand your basic algebra, Pythagorean theorem, and your trigonomic functions, sine, cosine, tangent. Those three. There's more functions, but those are the three basic ones. If you can understand those, then you'll be able to completely understand this proof that I'm designing. You just have to think a little creatively. So if we really delve into what this problem really means for us, we're solving a picture that looks like this. We have an equilateral triangle, which of course you know that means all the sides are the same, so I only wrote x for one side, but they are for all sides. Each angle is 60 degrees, all adds up to 180, standard triangle. And there's a circle inside, and all of the circle has 3 points that are touching the triangle. It's the biggest the circle could be in this scenario, and r is the radius. So in this problem, we're assuming we know r. We're saying if we have r, how can I get to x? Now you can take our final solution and reverse it back in terms of x to solve for r. If you have an equilateral triangle. But for this case, we're solving, if I have r, what is my x? What if I have the radius of the circle inside, what is the side length? So this is a picture of what we're doing here. Before I go on, I want you to take a few seconds here, pause the video maybe, and I want you to think about some creative solutions. How am I going to be able to represent r and x in the same equation? What am I gonna do this triangle to get them in a single equation? So you can pause the video and think about that for a few seconds. Okay, so coming back to this, you may be like, well, r is in the circle, the radius is of the circle, and x is the side length. How do those relate to each other? Well, here's the key part that we're going to try to figure out. Triangles are very special objects in mathematics. They have the Pythagorean theorem, trigonomic functions, similar triangles. They have a lot of different formulas we can manipulate with them. But to use all those, we tend to need to have the side length or an angle to work with. For example, Pythagorean theorem is a squared plus b squared equals c squared for a right triangle, or tangent, sine, or cosine are all representing angles. So to solve this, we're going to need to eventually make r either an angle or a side length. So that's kind of my motivation through going with this, is to make r a side length of a triangle. So how do I accomplish that? So when I look at this might be what one of your solutions was. When I look at this, I see 3 smaller triangles inside. And what's so special about this is inside of this piece right here connecting this is r. So if I cut this up, that's going to be a triangle here with the height of r. Isn't that neat? We just made r the height of the triangle. Now there's other ways to cut this up I can show you later. but that's my main motivation for splitting this up. So splitting it up, if we do that, what does this look like? Handy dandy diagram here. If we split it into 3 parts, we get this. Now, a lot of new information was just added, and I can explain how this got here. So the same x right here, this x on all sides, that's just the side length, same as before, same as this x. And this r right here I'm representing as the height of this triangle here. And I also added all these degrees. You see 60, 60, 60. That's where this 30 comes from. These 30s are just 60 divided by 2. I took this whole angle and split it in 2 triangles. And this 120, if you see right here, is a circle. And as we know from geometry, circles are 360 divided by 3. That becomes 120. So if we split these out, we're only going to need one of these triangles to work with. So I'm going to get rid of the other 2 right now. And I'm going to simply make it here. What this allows me to do, it just simplifies the problem. It really, we could do this for all 3, but why would you? So we're just going to single this one out here. And what we're going to do is we're going to say, let me enlarge this. We're going to say, okay, so you were talking about Pythagorean theorem, you might ask. You might ask me, oh, you were saying all this stuff, but those all require right triangles. And I would agree with you. And I'd say, well, if you look here, if we look here, this right here is what we got. We've got this, and these ones we can call this y. These are the same length with a height of r. That is a right angle. So what we can do is just what we did before, where we can split it in half and just take one of these triangles. And that's going to allow us to have r as a side length. So as you can see here, we just do that. We want to make it a right triangle. And keep in mind, when we split it in half here, that this x, we're splitting in half. So that becomes x over 2, right? So x over 2 now for each of these 2 sides. Because x over 2 plus x over 2 is just x. So now going back to this here, we do that, we split it, becomes x over 2. And then we can just put this triangle on its own slide. This is our split triangle. This is where we wanted to get to from the beginning. Remember, we wanted r as a angle or as a side on a right triangle to be able to manipulate it. So we're manipulating this now. And we've gotten this. So I want you to look at this next slide here. This next slide here is just a review of all that we did. As you can see here, we started out with an equilateral triangle, right? We split it, and then we got this piece, and we split it in half, and now we got there. If you have any questions, leave them in the comments. I'd be happy to ask about this. Also, you might have been thinking about another way to do it. You can also take this and split it along this axis. Say, oh, I want to make these 2 sides r and r, and this be x halves. That's fine to do this. So instead of breaking it up into 3 triangles, you break it up into 3 kites. And then the kites you'd split in half to this shape here. And then split it into this shape. So either way works. I wanted, for me, I split it into 3 triangles and then that into another triangle because I just didn't want to work with the kites because kites can be, they're not as easy to work with as triangles. But now that we got this piece, we really can start to solve our problem. So there's 2 methods that I came up with, me and one of my colleagues came up with, about how to solve this problem. The first method, we're going to be using 30, 60, 90 triangle properties. If you remember from your geometry class, 30, 60, 90 triangles are half of a equilateral triangle, which is what we had, half of equilateral triangle, which gives them special properties because we know certain side lengths about them. So before we begin, here's a little reference of what we just did. This was the whole PowerPoint before this, and we're just going to stick it up here just for our reference. Hopefully this will help. And this right here is our 30, 60, 90 properties. All for any u, which can be any variable or number. For any u, this holds true. So in our case, u is r. So if we plugged in r, this would hold true. And you can actually, if you do Pythagorean theorem on half an equilateral triangle, that's how you get all these numbers. So you can look that up if you want to see the proof for that. But I'm going to assume you already know this proof. So using this, what we can do is we can actually take u and let it equal to r. So if we plug it in, u equals r, 2u equals 2r, 3 square root u is equal to r square root 3, or u square root 3 is equal to r square root 3. And then we can just replace this with our original diagram. I went ahead and made a new diagram where we just replace this. You'll notice they are a bit different. We have the hypotenuse here, 2r, and we replace this x over 2 with this. And some of you keen-eyed viewers might notice something. These two triangles we just built are the same. But you notice there's nothing here because we don't know what it is, and there's a 2r here. Is there anything else that you notice that could help us with this equation? Remember, we're trying to find out what the side length x is equal to. So now I give you a moment to think there. If you notice, what's really cool about doing this method is we solved for this and this. These are the same triangle, which means this side length and this side length are the same. So that means these two numbers, whatever they evaluate it to be, are the same number, which means that x over 2 is equal to r square root 3. And that's the crux of this method. So using that, we can just say, oh, they're the same number here. They're equal. What this allows us to do is to do some algebra. So we can start with the equation we just found, which is r square root 3 is equal to x over 2. And what we can do from that is we just simply multiply the 2 over basic algebra. All we do is just r square root 3 is equal to x over 2. If we multiply by 2, those cancel out to be 1. Multiply by 2, that means x is equal to 2r square root 3. And that's as simple as it gets. We just broke down the entire equation here, triangle, and we got to this equation. Myself, I think that's pretty cool that we could just do that with a 30, 60, 90 property. Just not need any trig functions or anything like that. No complex numbers. Because seeing the diagram, I mean, if you look at this diagram here at the very beginning, you're like, how am I going to solve that? And you realize, wow, I can actually solve this just using basic geometry. So we get it in terms of r, and that's what we need. So if, let's say I had a 10-inch circle, or I had a 20-meter circle, whatever, the units don't matter as long as they're consistent. So if it was a 10-inch circle, that would be 20 square root 3 would 20 square root 3 inches would be the side length for each triangle of that equilateral triangle. So that's pretty cool. A second method, which I did not use, I used the first method, but my colleague came up with, is using trig functions. So as a quick reminder, sine, cosine, tangent. So you pick a theta and use these two. So since we have opposite and adjacent, we want to use tangent. which is opposite over adjacent for any theta. So you might say, what theta do we want to do this with? And to be honest, you can just choose either. Either works for this. But the thing is, using 60 is a lot easier because you have to do less algebra. So that's why I'm picking 60 in this example. So if we pick 60, that's our theta. I'm going to put this in the reference there. We can use this and we can say tangent of 60 degrees is equal to opposite over adjacent. And you say, you put it over x over 2 over r. Yep, because that's your opposite over your adjacent side of using 60 as your theta. So now we can just do some more algebra. I'll show you quickly what you can do with this x over 2 over r to make it a little bit nicer to look at. What this really is equal to is, we know that dividing two fractions, you just keep the first same and then change. So you're really multiplying by the reciprocal when you're doing this. So if we make this a fraction, r over 1, same number, r divided by 1 is r. We keep this the same, so we just multiply this number by the reciprocal of r over 1, which is 1 over r, which is just x over 2r. Now I'm assuming if you're watching this video, you probably know this, pretty easy, but you know, this trips me up sometimes. Basic algebra sometimes fleets your mind. But that's basically what I did here to make it a little simpler, and you'll see that. And then if we calculate tangent of 60, you might know this from your unit circle, you might have done it in a calculator, use Siri, whatever method you want to do. That's square root of 3. So here I wrote this like I just showed you. I didn't want you to be thrown off when I showed you that. So basically, this is tangent of 60, so square root of 3, and then this is what we just got. So I can rewrite it like this. This is what we just found. So using this, again, we can just do basic algebra. That's the nice thing about all these methods, is that it boils down to the algebra. It's a nice thing, except if you don't know how to do algebra. So doing this again, we can do square root of 3 is equal to x over 2r. And like before, you just multiply by 2r this time instead of 2. So cancel those out to 1, multiply by 2r, and then look at that, we got the same answer, which is 2r square root of 3. And then I can show you the math here. We multiply by 2r, we get that answer. So this is our answer to the problem. We solved it two different ways. I hope you enjoyed watching those, finding it those two different ways using those different proofs. And then there's one more thing, if you want to stick around. If not, if that's all you were looking for, thanks for watching. But I do have a little trick right here to solve using diameter and circumference if you don't have radius. Just because, you know, maybe you're measuring a pothole and you want to build a triangle around it or something, or a manhole or whatever, you know. I don't know. And you only have the circumference, you know, or you're like in clothing design, you need to measure someone's waist or something. Finding the side length using diameter and circumference. So I'll just run quickly through this. We know that this is our equation where side length is x, radius is r. How do we put it in terms of diameter and circumference? Well, diameter is easy. It's just 2 times the radius. So we just substitute for 2r, there we go. Diameter times square root of 3. Then circumference formula is just circumference is equal to 2 pi r. We just take out the pi, 1 over pi, and we get circumference over pi is equal to 2r. Substitute that. We get square c over pi square root of 3. Easy peasy, lemon squeezy. Let me make it a little easier for you to see there. So now If you want to, I have these practice equations. They're really simple because all you're doing is plugging into the formula. You don't really have to solve anything. Like I said from the start, this is one singular problem to solve. This is not really a technique you use to solve other problems. I'm just going to show you motivation and how to approach problems in mathematics. So if you want to solve these, you can. You can pause the video right now, and I'll let you do that. But that's not really the takeaway from this lesson that I'm giving here. This mathematical thinking. I'm more thinking about how did I approach this? How can you approach something? And I want you to think. Just want you to see the motivation, because a lot of professors and math teachers, they don't go through all that. They have their notes pre-planned. I have my notes pre-planned, and they don't go through their motivations. So I try to help you with the motivations here. Here's all the answers if you want to do that. If you stick it in a calculator, or if you just want to leave it simplified. And I mean, you could of course simplify the radicals. Like you could do square root. You could do 20 times 20 and then multiply it by the 3 to put it under the radical. That'd be a lot of work. I mean, here's the answer. Yeah. So there's the answers. If you made it all the way to the end, I want to say thank you for watching. Like and subscribe. I'm gonna try to put out. I'm a computer science major, and this is sort of my little passion project. I'm sort of dipping my toes into education a little bit. So that's why I kind of made this video. I didn't see any videos on it, like I said. And I'm gearing my channel more towards math, science, sort of STEM, maybe a little art, and computer science content, definitely. So if you like that, I'd like and subscribe. Please leave comments on how I did, if I did poorly, what I can improve. If you have any questions about the video, or if you saw a mistake, I'd love to hear that, because I'd love to revise it. And I'm going to be linking all the notes in the description of this. I do have a PDF where you can look at both the slides and the proof on how I did this if you have any questions. It's not a really big problem. The proof does go through a lot of my motivations in writing. But yeah, I just want to say thank you for watching. I hope this was interesting. Yeah, so I hope it was interesting. If you have any other questions, contact me in the comment section. I'll make sure to respond to as many comments as I can. And thank you for watching, and have a good day.